Hey everyone. In this video, I will be doing a Chapter 3 review. Chapter 3 is on data description. So, let's start with section 3.1, which is on measures of central tendency. What it means from this is that it's talking about the measures involved in the middle of distributions usually. It's talking about central tendencies, so like tendencies of kind of the middle of the group, or the center of the group, essentially, in the distribution. So, real quickly, sometimes you'll see the word statistics, sometimes you'll see the word parameter. And this is an important distinction for many topics in the class. The difference between a sample and a population. So a statistic deals with is a measure from a sample And when talking about the whole population, it's called a parameter. And remember, the population is like the whole group being studied, every single person in the group, whereas a sample is a specific number from that group, minus one. It just can't be the whole population. So, if we're talking about U.S. presidents, right? If I pool all U.S. presidents, that would be a population because it's every single one. But if I said a pool of 10 out of the 48 presidents, I don't know how many it is, 47, 48, something like that. If I said 10 out of that 47, that would be a sample. So, and this distinction appears constantly in statistics. This difference between population and sample. Sometimes it also does change the formula. So make sure, if you're ever getting a question wrong, you don't know why, maybe that's why. And in my questions, I always try to make it very apparent whether it's a sample or a population. Okay. So the first measure of central tendency to talk about is the mean. And the mean is just the average. So let's use a little bit of mathy notation here. So let's call how do I want to write this? Okay, so if it's a sample mean, this is denoted x bar. That's how this is pronounced. It's x with a line over it. It's called x bar. And the formula for x bar is x1 plus x2 plus x3 plus dot 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 plus x sub n over n, over little n. Right, this is just another way of doing the average. So the x1, x2, x3, dot 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 xn, we have to do it this way because we don't know how many values are going to be in the sample. Maybe there's 10 values in the sample, in which case n would be 10. When you're averaging a certain number of things, you have to, it differs depending on how many things there are in that sample. Right? If you've got 3 scores, you want to find the average, you add them up, and then divide by 3, right? The number of them. It's the exact same thing here. That's the mean, or aka the average. Very often we'll see this symbol right here. It's a capital sigma. And this stands for sum of all. And we're going to be doing some really big sums in this class over and over and over again, all the time. And so it can be convenient to you to also write this a different way, a more concise way, right? If I want to sum up all of the x values, I could just say sum of all x and then over n. Right? That's a more concise way of talking about adding up all of those values. But if that's really confusing to you, don't worry about it for now, I guess. But you really should get used to this symbol. When you see the symbol, just read it in your head as the sum of all, and it should help. That's what kind of made me help understand it, is just translate it as a set of words, sum of all, and it usually helps it make sense. So that's the formula for the sample mean. I'll put a little star there because it's definitely a formula we need to remember and memorize. I'll try to do that with the formulas we really need and use a lot. And we've also got, of course, population mean. And as first of all, the symbol is called mu. So it's another Greek letter, right? They're all Greek letters: mu, sigma, etc., etc. It's mu. So whenever you see, by the way, another little note. I think I mentioned this already, though. Greek letters are used for the population, whereas normal letters are used for samples. That's why we're using x in the sample notation and mu, which is a Greek letter, in the population notation. So the formula for mu, it's the exact same formula, right? The average doesn't change. The formula for the average doesn't change. I guess they do use big N, though, instead, to signify that it's not a sample, but instead the whole population. So they actually use a capital N. And again, the alternative notation for this would be the sum of all x over capital N. I guess I'll write here, let me just include, oh god, I hope you guys can't hear my dog snoring. Lily, please. Hey, shh. Let me put a couple notes here of the notation. So x1, x2, x3, all the way up to the xn are just data values. First data value, second data value, nth data value. Oh, and n, of course. Little n is the sample size. So the number of values in a sample set. Okay, and so I guess I got to put a note here of what big N means then, so that I've defined all the symbols. Big N is the population size. And of course, this is another very important formula, so let me put a star next to it. Okay, so I got an example here. I guess this is a sample, but again, it doesn't really matter for mean since the formula is the same either way, whether it's a population or a sample. You know, it's just the sum of them all, and then you divide it by the number of data values. So, for example, here we've got the number of confirmed flu cases for a 9-year period is shown. Find the mean. And it's got, let's see, well, it said a 9-year period, so I would assume there's 9 data values. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, there's 9 data values. Let's just point out everything. So in that case, N is 9, right? And so N equals 9. This would be our x1, x2, x3. I'll just label them all, why not? All right, so I've labeled all the data values with their x sub number variable, x sub 1, x sub 2, x sub 3, etc., etc. And now we know what everything is, everything stands for. And remember the mean, which I'm assuming this is a sample, so x bar. It's, I won't use the summation notation, I guess. x1 plus x2 plus dot 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 plus, in this case, x sub 9. Right? Because that's what our n is. That's the last data value in the sum. All over n, which is 9. Okay, so that's 4 plus 46 plus 98 plus all the way up to 62. Let me see what that sum is on my calculator. So I just got to add all these up. 4 plus 46 plus 98, 115, 88, 44, 73, 48, and 62. So that numerator is 578. And then we're dividing this all by 9. So I could take this, divide it by 9. It says 64.222. So I guess rounding in this class, you know, what was that? I probably won't be too picky about it. Like 1 decimal is probably good, but 2 decimals to be safe, I guess. So 0.22. And that would be our answer here, and that would be the mean. Okay, so this is for ungrouped data. That example that we just did, but we can also have grouped data. And this does change the formula for the mean around. So for group data, it might be an example. Let me just pull up an example here real quick. Okay, so here I've got an example of a set of grouped data. So we don't have the raw data. We just have this set of grouped data. In the first class, so it says the frequency distribution shows the salaries in millions for a specific year of the top 25 CEOs in the U.S. So it would seem that there's 13 individuals who had a salary between 15.5 to 20.5 million, but we don't know exactly what that salary was. It was just in that range. And so since we don't know the exact data values, finding the mean is a little bit more difficult. We have to have a formula that uses the midpoints. Okay, so I'll say here, since we only have this grouped data, right, and not each individual data value, we have to use a different formula for the mean. Okay, and the formula is x bar is equal to the sum of all the frequencies sorry, I need a parenthesis here. The book doesn't have it, and it's really annoying. The sum of all the frequencies times their midpoint, all over n. So another formula you want to know, there's going to be a lot. It's kind of just the nature of statistics. You have to have formulas. You have to memorize formulas. So in this case, let me write a note here. F is frequency of class. And x sub m is the midpoint of the class. Okay, so essentially you take the frequency, you times it by the midpoint of the class. That kind of averages all of the data in that class, and weights it according to the frequency in a way. And then we sum them all up and divide by the number of data values, which is n. And remember, in this case, I guess one more note, because how do you know what n is if you don't have this total, right? So here it does have the total, so n here is 25, but it doesn't always. So in this case, it's the sum of all the frequencies. N is going to be equal to the sum of the frequencies, right? Because 13 means that there were 13 people that had a salary between 15.5 and 20.5 million. And then the 6 means there were 6 people. The 4 mean 4 people. 1 and 1 means there were 1 people each for those classes. So we add them up. That gives us the 25. And it also mentions here it's a frequency distribution of the top 25 CEOs. So n is always the sum of the frequencies, in case that ends up coming up in a question. So now that we have this formula, remember it's the mean for grouped data formula. Now we could go ahead and do this question. So we do want to have a couple more columns here to help us with all the data, right? Because now data is starting to pile up, and we really want to make sure we organize it so that we don't get confused, because you get one data value wrong and it's going to throw everything off. So you have to be really careful, really organized. So I'm just going to copy the first 2 columns here. I guess I could pause it while I'm doing this. Okay, so I've copied the data down from here, and I added 2 new columns, one for the midpoint and one for the frequency times the midpoint. And then I'll have all these data values that I could sum up, which I guess I'll put down here. And then we could divide that value by n, and that will be our x bar, our mean. So how do we find midpoints? Well, it's essentially just averaging the 2 limits. So you add them together and then divide by 2. So I guess let me put that here as well. So the midpoint of 2 things is you add them together and then divide by 2. It gives you right in the middle. So for the first one, we've got to do 15.5 plus 20.5, and then divide that by 2, and we get 18. I know the next one is... I know the class width here is 5, so I know the next midpoint, I just have to add 5, and it'll get me to 23. But again, to get that, you could also just do 20.5 plus 25.5, and then divide that by 2, and you see we get the 23. So next one will be 28, 33, and 38. And so now in the next column, now that I've got the values that I need to multiply together, in the last column, I'll put their product, and then I'll add all those products together. I know it's very monotonous and tedious, but you really do want to do this for these questions, or else you're going to find yourself getting it wrong, and you're not going to know why. Here, you'll at least know, if you get it wrong, you know how to go back and figure out why. Like, if it's some really weird number that you know is wrong, you know you messed up, oh, I could go back and check out, see what happened. So, first entry here, 13 times 18, right? F times the midpoint, the frequency times midpoint. This one we get 234. 6 times 23. 138. 4 times 28. 112. And then 1 times each of these values are just going to be those values themselves. And now, the numerator of this formula, right here, is the sum of all of these, right? That's all that really is saying. Sum of all the F times the XM. Okay, I've got the F, I've got the XM. That's the F right here. And this is XM. And so here's F times XM. And we want the sum of all F times XMs. So I'm going to take the sum of this column right here. That will be the numerator of our formula. So what do we get? Trying to figure out what color to use. Let's see, I gotta add all these and divide by, remember, in this case, n is 25. That's the sum right here. Remember, the sum of the frequencies, that's our n. So 234 plus 138, 112, 33, and 38, and I'm dividing it by 20. Well, let me do that in a sec. So this is actually 555. So our answer, the mean in this case, is, remember, here's the formula, the sum of all the frequencies times their midpoint over n. So the sum of all the frequencies, that's what I got right here, that's the 555. And the n, that's 25. And then finally doing this calculation, we get 22.2 exactly. And so you could be asked 2 different questions to find the mean. Either you've got the full set of data just there, the raw data, or you've got the data in groups where the amount is basically based on the frequency. And then use this formula for the mean. Okay, so that's the first measure of central tendency. Mean, right? The mean, that's a measure of central tendency. It's kind of trying to figure out what the data is doing on average. That's what the mean is. You could either find it from the sample or from a population. It's the same formula, the sum of all the x's over n. Or it could be group data, where it's the sum of all the frequencies times their midpoint over n. Okay. The next thing I want to talk about here is the median. And the median is the literal middle of the data. So the median is basically the midpoint of the data array. And so you do need to sort it from low to high. Let me show you guys the step-by-step process to find the median. Because it does change depending on whether there's an odd or even number of data values. So step 1 is arrange the data in ascending order. 2, find n. Remember the number of data values in the sample set, in the data set. And then depending on if n is odd or even, there's 2 different ways that you need to find the median. So A, if n is odd, select the middle data value. Right? If there is an odd number of values, like 5 or 9, there's an exact middle. The middle of 5 data values would be the third one. Middle of 9 would be the fifth one. But if there's an even number of data values, so if n is even, then we've got to find the mean of the 2 middle values. So I'll just write here, find the mean of the 2 middle values. Right, for example, if there's 6 data values, 1, 2, 3, 4, 5, 6, there's 2 middles, the 3 and the 4, and so you have to average them together. Of course, average being you just add them together and divide by the number of them, which is 2. Okay, and that's how to find the median. Pretty not so bad. Let's just use this data set that we had here for an example. So let's just say I copy that same set of values here. Okay, and we want to find the median. Well, it's not sorted, so we've got to first sort it in ascending order. So let me write here, sorted, ... So we've got 4, 44, 46, 48, 62, 73, 88, 98, 115. That's all of them, right? Yeah. Okay, so now I've got them sorted correctly. And in this case, n is 9, right? Yeah, it's 9. Here's the first value, second, third, fourth, fifth, sixth, seventh, 8, 9. And so as you guys can see, the middle data value, which is the 5, has 4 data values to each side of it. That's kind of how I find the middle one fast. It has an equal number on each side if it's odd. So in this case, the median is 62. Okay, and that's the median. The middle of the data, the mean is definitely, I think, more important because it tells us about all of the data, whereas the median just tells us about a certain part of the data. So the median doesn't really get used that often. Nor does mode, which is the next one to be aware of. And the mode is the data value that appears the most often. So again, you want to arrange them in order. And there can be more than one mode if there's a tie amongst data values that are appearing the most. So let me pull up a quick example here from the book as well. Where is it? Sure. How about this one right here on public libraries? And it's asking us to find the mode. So, again, it is helpful to sort them. I guess you don't have to for a mode, but you pretty much do have to for a median. Okay, so 21, then there's 77 twice. 101, 114, 159, 311, 382. And so I do see one that appears twice, namely 77. Nothing else appears twice because if something else appeared more than once, since it's now sorted, we would get it repeated back to back, but that doesn't happen anywhere, only at 77. So in this case, the mode is 77. But, say 159 appeared twice as well, then there would be two modes, 77 and 159. So there can be, multiple modes. They just have to appear the same number of times, aka the most number of times. Because remember, the mode is the data value that appears the most often. Okay, so we've got two more measures of central tendency I want to mention. We've got mid-range, which kind of tells us it's the high value minus the low value. The middle of the data, I guess, is in a way another way of measuring the middle of the data. And so the mid-range, the definition is just the formula. So the formula is that mid-range, MR, is the lowest value. It's the average. Oh, I'm sorry. I was mixing it up with range. Mid-range, sorry, I misspoke. It's not the highest value minus the lowest value. That's range. Mid-range is the lowest value plus the highest value over 2. So it's the average of the lowest and the highest values. And it's a rough estimate of the middle. So if you see MR or mid-range, that's what that's referring to. Again, it helps to sort the data, but I guess you don't really need to. You just find the lowest value and the highest value. So, again, let me pull up another example from the book here. Oops. Got to move a little bit ahead first. So this one right here. They want us to find the mid-range for the number of bank failures, whatever that means, for a recent 5-year period. So remember, mid-range is the average of the low and high values. So what's the lowest value here? Looks like it's 3. And the highest value, 157. So therefore, the mid-range is 3 plus 157 over 2. That's 160 over 2, which is 80. Okay, that's mid-range. And we've got one more called weighted mean. So I guess I should put another star here because there's 5. Let me see. Yeah, I've got 1, 2, 3, 4, and then this last one, the weighted mean. So sometimes certain data values are more important than others. For example, if you're trying to find your GPA, some credits are 4 credits, some classes are 4 credits, some classes are 3 credits. And so the formula for the mean needs to take into account how much each class is quote unquote worth, or how important each class is, how big its contribution is to the total average. So that's when we use weighted mean in situations like that. And let me see what the formula is here. It's x bar is equal to, so it's W1 x1, the weight of the first data value times the data value, plus, and then you do the same with the second data value. You take its weight, you multiply it by that data value, and we sum all these up. So dot 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 here plus Wn sub xn, and we divide this sum, by the sum of the weights. So it's W1 plus W2 plus dot 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 plus Wn. This is the formula for weighted mean. It's the sum of the weights times their data value divided by the sum of the weights. Another way, the concise mathy way of writing this is the sum of all the W times X over the sum of all W's. And so this is the 5th formula from this section that I definitely want you guys to memorize. So let's look at an example for this as well. I believe it is an example like I mentioned. So it says a student received an A in English, which is 3 credits, a C in psychology, which is 3 credits, a B in bio, which is 4 credits, and a D in phys ed, which is 2 credits. Assuming an A is 4 grade points, B is 3, C is 2, D is 1, and F is 0, find the student's grade point average, right? Where a 4 would mean that they average an A. And I guess a 0 would mean they average an F. So let's put all the data together. Yeah, I guess I'll just put your class. Grade. And the number of credits. Well, I should put the weight first, which is the number of credits, right? The value is the grade. So, yeah, I'll just put your weight and the grade. So let's see, English. Which is 3 credits, so that's our weight. And they got an A. And remember, an A is worth 4 points, so I guess I'll just put in parentheses here a 4. We've then got psychology. 3 credits, and what they get in that, a C, which they mentioned is 2 grade points. What else? Bio. just 4 credits they gotta be in. That's 3 grade points. And there's, I think, one more, right? PE, which is 2 credits, and they got a D, which is worth 1 grade point. That's it, right? Yes. So remember, these are the weights, and these are the data values. So the mean which is, well, actually, we want a couple, let me put it down here, because we want a couple more columns here. Remember, it's the sum of the weights times the data value over the sum of the weights. So we want a column of weight times data value. So I'm going to add one more column here. Oh, they actually didn't even do that in the book, but I think it's very good to do. So this is, remember, W times X. This would be W1 times X1. Okay, that's 12, 6, 12, 2. So what's this sum? 24, 32. And let me also, here I'll put the W and the X here because I want to get the sum of the W's because I need that value as well. 3, 6, 10, 12. Right? This one right here is the sum of the weights times X. And this one right here is the sum of the weights. So we get 32 over 12. Which is 2.67. Let's round it to 2 decimals. 2.67. I guess if it was 1 decimal, it'd be 2.7. So that's the weighted mean, and that's the last measure of central tendency. Okay, so with that, let's move to section 3.2. I believe we covered everything in 3.1 that I want to. Chapter 3, this is a lot longer now. Chapters 1 and 2, that's a lot of more conveyance material and organizing stuff and things like that. So, we could get through those pretty quickly, but in Chapter 3, we start to really get to the formulas, and so these review videos are pretty long because I really want to make sure I go over everything we need to. Okay, so section 3.2. And 3.2 is on measures of variation. So what does that mean? It means how much the data varies. Or how spread out is the data. Right, so a dot plot is pretty helpful here. Let's say we've got 2 different data sets, right? And this is one data set. Okay, so I've got one data set here where it looks like the data is pretty close together, right? And maybe I'll have another data set here. I'll have the same number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one had 10, so I want this one to have 10 as well. 1, 2, 3, 4, 5, 6, 7, 8, 9. One more, 10. So if you saw these 2 different data sets and you were to ask, which one has more variance, which one is more varied, It's asking about how spread out the data is. That's what variance is talking about. That's what this measure of variation is talking about. The one on the left, this is something with low variance. Right? The data do not vary very far from each other. They don't. There's not a lot of spread in the data. They're not very different from each other, right? They're not very different from each other. That's kind of the most important thing. These ones have high variance because it's very spread out, very different from each other, that sort of thing. Okay, and so in this section, we'll define a couple of measures that help us discuss how much variation there is in the data. The first one being range, which I mixed up just a second ago, remember? Remember, the range is the highest value minus the lowest value. So it tells you how big the range is that you'll find the data in. It kind of tells you the width of the data almost. That's kind of how I like to think of it. That one's pretty easy to find. I probably don't even need to do an example there. But then we do come to the formulas for standard deviation and variance. And there's two sets, one for population and one for a sample. So it can be pretty confusing. And so let's first talk about population variance. Okay, so remember, it's a population measure, so it needs a Greek letter. For this, they use a lowercase sigma. And actually, population variance is a squared data value. So population variance is actually, it's called sigma squared. I'll write under 2. Sigma squared So when you hear me say sigma, you know what symbol I'm referring to. And the formula, which you do need to memorize, so again, I'll put a star here. It's the sum of all the x's minus mu squared over big N. Let me just write one more parentheses in here to avoid confusion. The sum, you do the squares and then you sum them up. So I want to, let me just write a little nicer. The sum of all the value minus the mean, and then you square that. Okay? So this is the formula for what's called variance for a population. X is the value. Mu is the population mean. Remember, we've discussed that value before, that symbol rather. Big N is the population size. And then we've also got what's called the standard deviation, which is just sigma. So, right here, population standard deviation. So this is just sigma. And if sigma squared is that thing, then sigma is just, you take the square root of each side, essentially, right? If we took the square root of sigma squared, it's just sigma. So sigma ends up being, you just add the square root on this right term. So it's not too much, it's not too much harder on the memorization, right? As long as you know sigma squared, you know sigma is just attaching this big square root symbol to it. That would be our formula for sigma, aka the population standard deviation. Okay, so let me just make up my own example here, I guess. I'll say here, find variance so I'll just make it up. How about this as the data? 4, 62, 30, 12, 20, 9. And let's just assume it's a population because that's the formula that we're learning. Right now, we'll learn about the sample formula in a sec. But let's say this is the data from a population, and we want to find the population variance and population standard deviation. So, or well, let me put the data in a chart first. So, here's the data value, which remember is just x. What do I put on the side of this? Well, okay, let me just put the data out first. 4, 62, 30, 12, 29. Okay, so let's look at the formulas. Remember, sigma squared is the sum of all the data value minus mu squared over n. Okay, so let's make sure we know everything and we use the chart accordingly. So these are all our x values. We've got x1, x2, x3, x4, x5, x6. And again, there are 6 data values. That's our n, right? So we know n is 6. So we have n. We have our x's. What don't we have? There's only one thing, mu, right? And remember, what's mu? It's the mean. And we have our formula for the mean. Remember, we just add the data values up, divide by the number of data values, which in this case is 6. So it's 4 plus 62 plus 30 plus 12 plus 20 plus 9, whatever that numerator ends up being, all over 6. You have to do all the numerator addition first, then hit enter, and then divide by the denominator. So 4 plus 62, 30, 12, 20, and 9. So that numerator is 137. When I divide it by 6, it gives us our mean, which is 22.83. Let me round it to 2. Or I guess I could just leave it as 137 over 6, but for convenience, let's just do it this way. It's not going to cause any issues. So very often, I like to put in a column for mu. And I'll just put the same value here every single time. It's 22.83. You'll see why in a second, because the next column, I'm just going to do x minus mu. And so it'll just be the column, the first column minus the second column then. And it'll be really easy to kind of handle. Why am I putting 30 there? 22.83, 22.83, 22.83, 22.83. And so in this column, I'll put x minus mu. And then the column after that, I'll put x minus mu squared. And then that numerator of our mean, I'm going to be able to find right here by summing up this last column. Right, that will be this numerator right here. And so that will help us with that difficult calculation. So what do we get here? 4 minus 22.83. It's negative 18.83. It's a negative value, but it's going to end up getting squared in the next column anyway. Whenever you square a value, it becomes positive, no matter what, right? Two negatives multiplied together make a positive. Two positives multiplied together make a positive. So that's one reason behind the squaring, actually. Let's see. So we've got then 62 minus 22.83, which is 39.17. So we just keep doing this over and over and over again. 7.17. As you can imagine, Excel is very good when there are a massive amount of calculations. You don't want to keep doing it by hand, right? But these are enough that we could just do it here by hand and pray not to mess up. The last one is 9 minus 22.83. Oh, I wasn't showing the calculations the whole time. I'm sorry. And then I guess I should keep this on the left then. Negative 13.83. And now what do I do in the next column? I just square the previous column, because this column I just filled in is x minus mu. That's the value that I have to square. So I guess I could have also done that all at once, so I didn't have to input these every time, but it's fine. So no, I need to put these in parentheses, but whatever. It's just going to be the positive of it anyway. Okay, negative 18.83 squared. 354.5689. Let me pause and finish the rest of these. Okay, so I'm done doing all the values of x minus mu squared. Right, I'm just squaring this column and then writing it down in the next column. And then here in this yellow box, I've got the sum of all of those. Remember, that's the numerator of our sigma squared formula. So let me go ahead and we can find sigma squared now, right? It's the sum of all the x minus mu's squared over n. So we get this 2256.8334 value. All over n. Sorry to brain fart for a second. And in this case, n is 6. So what do we get here? This value divided by 6. 376.1389. And that would be our variance for this set of data, right? The 46230, 1229 data set. And remember, standard deviation is just the square root of variation. This is the variance. So if we want, right, I asked here to find the variance and standard deviation. Okay, so here's our variance. That's this value. I encourage you to confirm this yourself. You know, do this yourself along with me to make sure you're getting the same values on your calculator, because a lot of people have calculator errors and issues that they deal with. And also, what's our standard deviation going to be then? It's just the square root of sigma squared. So it's the square root of this value, 376.1389, which I've still got my calculator right here. And it gives us approximately 19.39. And remember, this is what's called our standard deviation. We'll learn a lot more about the influence of these measures later. Because, what does this 376 value mean? What does this 19.39 value mean? Well, the 19.39 value, that kind of is actually, it's the average distance away from the mean, essentially. Essentially is what it's trying to do there. Right, it finds the distance away from the mean, which is x minus mu. It squares it to make everything positive. And for other reasons too, that I don't, completely know. And then you divide them all by n. And then for the standard deviation, you just square root that value. So just double check that you could come up with all these same values. It's very, very important. Okay, so very important formulas here. You have to memorize these. I know they're not fun to memorize. Get a lot of practice with them. Hopefully, you do get a lot of practice with them in the homework and stuff like that. And do well in your quiz on this stuff. So that's the formulas for population and for standard deviation and variance. But there are also formulas for samples for those same measures. So let's talk about those as well. The formulas are extremely similar. So if you remember the population ones and you remember the differences in the sample ones, it's not too bad, but I know it is pretty, it's not easy memorizing all these formulas. So for sample variance, this is denoted with s squared rather than sigma squared. Remember, samples use English letters, populations use Greek letters. That's, again, one good indicator of what your kind of what framework you're working in. Anyway, the formula is the sum of all the data value minus the average squared over n minus 1. So the difference between population and sample, number one, this is x bar instead of mu. But remember, they represent the exact same thing, the mean. It's just what letter you refer to it according to what domain you're working in, sample or population. So that's still the mean. So the numerator is the exact same. It's just the names are different. But the denominator is different. It's n minus 1 rather than n. So, that does actually change rather than just the name changing, right, from big N to little n. It's n minus 1, actually. So very similar to the population variance formula. You just have to replace the name of the average from mu to x bar, and the denominator, you stick a minus 1 on it. That's how I remember it, at least. And the formula for standard deviation, you might guess it for a sample. Well, it's just s, and what's s? It's the square root of s squared. So it ends up being the square root of whatever we've got here on the right side. Sum of all the x's minus x bar squared all over n minus 1. And this is how to find the standard deviation of a sample. Okay, so we might as well get an example in, a concrete example in. I'll just copy this one from the book here. So I've got this question here from the book. The number of public school teacher strikes In Pennsylvania, for a random sample of school years is shown. Find the sample variance and sample standard deviation. So, of course, one very good indicator of whether it's a sample or a population is if it's just straight up telling you. So it's telling us here this is a sample, so we've got to use the sample formulas. And I usually do that in all of my quiz and test questions. I'll just straight out tell you whether it's a population or a sample. I don't want there to be confusion over that. Or ambiguity over that. Okay, so again, there's 6 data values here, so very similar to the one that we just did where I made up the values actually. So let me put everything again in a table. So we've got here 9, 10, 14, 7, 8, 3. And what's our formula here? That helps me figure out what I need in the columns. Remember, s squared is the sum of all the x minus x bars squared over n minus 1. Okay, well, n is 6. In this case, right, 6 data values. We know n. And what's x bar going to be? It's the average of all the data values, so we got to add these all up, divide by the number of them, which is 6. 9 plus 10 plus 14 plus 7, 8, and 3 over 6. Which is 8.5. I'm cheating. It's 8.5. So now we know everything we need for our formula. We've got all the x's. We've got x bar. And we know what n minus 1 is. So we can now come up with all the columns we need. So I'll put a column here for x bar. It's 8.5. It's always 8.5, so it's the same in every column. The next column will just be x minus x bar. Right? I'm kind of building up this summation. First I have x, then I need x bar, so I have a column for that. Then I need the x minus x bars, so I have a column for that. Then I need the x minus x bar squared, because I'm going to sum them all up. So I ultimately need a column for that as well. Let me move this down here. So what do we have here? This will be 0.5. At least I can do these ones in my head. It's not an ugly decimal. They were nice here for that reason. Let me not mess up. So 10 minus 8.5, 1.5, of course. 14 minus 8.5 is 5.5. This one's negative 1.5. This one is negative 0.5. And 3 minus 8.5 is negative 5.5. Remember, in the next column, we got to square them, whatever was in the previous column. So 0.5 squared, that's 0.25. 1.5 squared, it's 2.25. 5.5 squared, 30.25. Negative 1.5 squared, 2.25. Negative 0.5. I should put that in parentheses. I did that one already. I forgot to square it. Negative 0.5 squared. It's 0.25. This last one's going to be 30.25. Okay, and we're going to need the sum of all of these x minus x bar squared. So let's add these up. 0.25 plus 2.25 plus 30.25 plus 2.25 plus 0.25 plus 30.25. It's 65.5. So What do we end up getting here for our variance? It's 65.5 divided by n minus 1. Remember, n here is 6, so n minus 1 is 5. So 65.5 divided by 5, it gives us a variance of 13.1. Remember, that's s squared. S squared is 13.1 in this case. And that's our variance. And what would our standard deviation be? Remember, that's s. Let me just write here variance. Variance is s squared for a sample. S, that's standard deviation for a sample. It's just the square root of that. So square root of s squared, that's square root of 13.1. What's this? 3.62. 3.62 should be good enough. And remember, that would be our standard deviation in this case. Okay, so there also can be, again, we could have the data grouped rather than having all the raw data. And there probably is a formula for population as well, but we're only going to study the sample formulas for variance and standard deviation for grouped data. So only for sample in these ones. So for grouped data, s squared, remember the variance. It's not a nice formula, guys. It's n times the sum of all of f times xm squared minus the sum of all f times xm squared on the outside of the parentheses, all over n times n minus 1. Not a nice formula. A very ugly, horrible formula. I probably won't have you guys memorize this one. Like, if I put this on a test or quiz, I'll include the formula in the question or something like that. But I'll put a star next to it anyway, because it is an important formula. And also, the standard deviation for group data, again, since it's s and variance was s squared, it's just the square root of s squared. So it's the square root of this whole thing that I have here. N times the sum of all the f times xm with the xm squared on the inside of the parentheses, minus the sum of all the f times xm with the squared on the outside of the parentheses, all over n times n minus 1. So, they're really not nice formulas. I totally get it. We'll do one example together. Okay, so I've got here an example of such a question. It says, find the sample variance and the sample standard deviation for the frequency distribution of the data shown. The data represent the number of miles that 20 runners ran during 1 week. So, and they're also kind enough to provide us the midpoint here as well, it seems. Okay, so again, let me just copy these formulas here. Let me s squared, I guess, that one. That's the one I really want. Okay, so what are we going to want in our column? Well, and let's pick out everything. So what's n in this case? Remember, n is the sum of the frequencies, so I've got to add these up. Let's see, that'd be 3, 6, 11... 15, 18, 20. Yeah, and it also says that there's 20 runners, so that checks out. So our n is 20. So we know n minus 1. So I guess we'll want a column for xm squared. a column for f times xm, and then a column for f times xm squared. And that should be about enough. Let me copy this here. I'll be super lazy. Okay. So I need some more columns, right? What do I need here? This is our f. This is the midpoint, so this is x sub m. I guess we want xm squared as well. So let's have a column for that. We also want a column for f times xm squared. And that will help us come up with this summation. We also want, so we're going to have a lot of columns here. We also want a column of f times xm, this right here. And then we can square that as well. Okay, so let's just go ahead. Let's keep going. So xm squared. Let me just move this over. This will be 64, 169, right? Is 13 squared. Yeah. 169. I don't know what 18 squared is. 324. 23. 529. 28. 784. 33. 1089. 38. 1444. Okay, anyway. So now in the next column, we're doing f times xm squared. That's this one right here. So it's essentially these two columns. We're just multiplying them together, and that'll go here in each row. So this one is 1 times 64. That's just 64. This one is 2 times 169. 338. 3 times 324. 972. Okay, let me just cheat for the rest. 2645. 3136. 3267. 2888. So we've got this summation that we're going to need. It will be the sum of this column right here. So that's one of the summations check. Essentially, you want a column for every summation. Sometimes we have other columns to build up to that summation column. Okay, so what else do we need? This one. So we need f times xm, and then to square it. And then add all those up. So I'll put f times xm here, and then here I'll put f times xm in parentheses squared. So this one is 1 times 8, that's 8. 2 times 13, that's 26. 3 times 18. This is 54. 115. 112. 99. 76. Guys, I messed up the formula. Let me go back and change this. Oh my gosh, sorry. The stupid parentheses in this book always throw me off. It's really annoying. My apologies. So this term I had wrong. So this is parentheses. That's why you kept seeing me wrinkling my face, probably. It's the sum of all the f times xm's, and then we square it. So my mistake, guys. Please make sure to correct that. Really sorry about that. This book with the parentheses always throws me off here. Okay, and so this one's parentheses, sum of f times xm, and then squared. Very sorry about that, guys. So this one's wrong here as well. That's all I had wrong, is I put the 2 on the wrong spot. Sorry about that. So it turns out I don't need this column. I just need these 2. Okay, so, and then I'll have to square whatever this is in a later step. So the sum of all the f times xm squareds, that's going to be the sum of this column right here. 64, 338, 972, 2645, 3136, 3267, 2888. Okay, so this sum is 13,310. Remember, this is referring to the sum of all the f times xm squareds. Right? Because every entry in this column was f times xm squared, and then we sum them all up. And this one right here, the sum of all the f times xm's, let me add these up. 8, 26, 54, 115, 112, 99, and 76, which is 490. And remember, this is the sum of all the f times xm's. We haven't squared that value yet, like we are going to need to in the formula. Okay, so here's our formula. We've got all the values that we need now. We've got those 2 summations. We know what n is. Let me just copy here. Copying the formula down here. So what are we going to get here? N. Remember, it's the sum of the frequencies. Again, in this case, it's 20. We said that earlier. I know it was a while ago. So we get here 20 times the sum of all the f times xm squareds, which we got right here is 13,310, minus the sum of all the f times xm's, which is 490 squared, all over n times n minus 1. N is 20, so n minus 1 is 19. 20 minus 1, right? And so this is what we're going to have to use to calculate our variance here. Let's see. 20 times 13,310. 266,200 minus 490 squared, whatever that is, 240,100. And this is all divided by 20 times 19. You've got to do correct order of operations, right, guys? Or else you might have some issues with these calculations coming out wrong. So we got to do the numerator first. 266,200 minus 240,100. It's 26100. And this is divided by 380. Which is finally 68.68. Okay? And again, remember, this is s squared We were looking for variance of grouped data here. This is the variance. It was a different formula because it was grouped data. And then S is just the square root of this. That's our standard deviation. Let me use the exact value here, the pre-rounded value, so that I get a more accurate answer. Right? If you round and then use the value, you've lost a little bit of accuracy. But if you round at the very end, that's how you don't lose accuracy. So I'm saving the rounding to the end by putting here the full answer and square rooting that, and now I'll round. If it'll let me hit enter here. 8.29. What I said was 8.29. And in this case, this is the standard deviation. Okay, there's two more things I want to mention in this section. It's Chebyshev's theorem and the empirical rule. These could be a little bit hard to grasp, not knowing much about what standard deviations mean practically. I'll try to draw pictures here to help. Okay, so Chebyshev's theorem. Chebyshev's theorem says that the proportion of values from a data set that will fall within K standard deviations of the mean is, so the form is at least, so I guess I'll put here a less than or equal to. That's how you say at least, right? At minimum. One minus 1 over K squared. Where K is a number greater than 1. Okay, so K has to be greater than 1. So, let me think of an example here real quick. Okay, so I think the way that I want to explain this is to use a couple different Ks and try to explain them graphically. Let's pick for our first K 1.1. Because remember, it has to be a value. K is a number greater than 1. It has to be bigger than 1. It doesn't work for 1. So we need to go a little bit bigger than 1. How about 1.1? We'll try that first. So if K equals 1.1, we get that the proportion of values from the data set that will fall within 1.1 standard deviations of the mean is at least 1 minus 1 over 1.1 squared. So this ends up giving us 0.1736 or 17.36%. So that gives us a minimum, a floor of the percentage of values that fall within 1.1 standard deviations. We know it can't be less than this. So let me show you a picture here. Right? Let's assume we've got some random distribution, something like this maybe. It's a little skewed to the left. We know that let me draw just a normal distribution for convenience. We know 17.736 of the data falls within 1.1 standard deviation. Wait. How do I want to say? No. I drew the picture a little bit wrong. I'll correct this. So the mean is going to be right here. And we'll say that... So if we go out one standard deviation in each direction, so if this is like one standard deviation, two standard deviations, right? Chebyshev's theorem says that 17... By the way, this says 1 SD, 1 SD, 2 SD, 2 SD. I know it's a little sloppy, hard to understand. But I guess 1.1 standard deviations then would be right around here or so. And what this is saying is that at minimum, this distance is going to be 17.36%. At minimum, 17.36% of the data will be within these two spots. Oh wait, I meant to go to that one actually, the one further, like that. So essentially, at minimum, 17.36% of the data will fall between these two spots. Okay, let's try a different K. How about 2? Because that's a normal number of standard deviations to look away from the mean. So what do we end up getting for the percentage of values that fall within 2 standard deviations? Right? It's 1 minus 1 over k squared. K in this case is 2. So this gives 1 minus 1 over 4, which is 4 over 4 minus 1 over 4, which is 3 over 4, aka 75%. So Chebyshev's theorem says that at minimum, 75% of the data will fall within 2 standard deviations of the mean. So let me draw another picture here. I'll try drawing this one a bit skewed. Let me draw a little bit better. There, that's pretty good. So let's say the mean would be like here. Right? Chebyshev's theorem is for any distribution, any shape. That's why it's at minimum instead of equal. We'll talk soon about the empirical rule, which is for normal distributions only, but we get a much better approximation of the data. So we'll talk about it in a sec. So here's mu, right? And if k is 2, we're going to encompass 75% of the data. So if I were to go out 2 standard deviations in each direction, so say like this is 1, 2 standard deviations to the right of the mean, and this is 1, 2 standard deviations to the left of the mean, Chebyshev's theorem says that 75% of the data is going to fall between these values. So, say it's height or something. Most people are 5'9". And say the standard deviation is 2 inches. So we want to see how many people would be within 5'9" plus or minus 4 inches. And that would be 75%. 75% would be in that range, at least. That's what Chebyshevs would say. So if it's height or something, right, it would say 75% of people are between 5'5" and 6'1" in this example that I've just made up, where the average or mean, mu, is 5'9", and the standard deviation is 2 inches. So if we go at 2 standard deviations to the right, we add 2 inches twice. It'd be 5'9" plus 2, that's 5'11", plus another 2, that's 6'1". So that would be the right boundary. And the left boundary would be 5'5". So 75% of people would be between those. The other 25% would be on the two tails. They would be either really, really tall people or shorter people. That would encompass that 25% range. So this is what Chebyshevs is doing. It's giving us a minimum for the amount, the percentage of values within the number of standard deviations away from the mean. Let's do one more. If k is 3, we would get what percentage of values would fall between 3 standard deviations away from the mean. This will be 1 minus 1 over 9. It's 9 over 9 minus 1 over 9, or 8 over 9. What's 8 over 9 as a percentage? 88.89. So that's how we get this value of at least 88.89% for 3 standard deviations for any size distribution. Again, let me draw one more picture here. Say we've got a distribution. I don't want to draw it normal. Let me draw it skewed again. How about this one? The bead's not going to be in the middle of this. It'll be a little bit to the right because there's a lot of values over here that are going to kind of drag it to the right. So I'll put it like right here. This is mu. And we know 88.89% will be within 3 standard deviations from the mean in either direction. 3 standard deviations to the right or to the left. So let me say this is 1, 2, 3 standard deviations to the right. 1, 2, 3 standard deviations to the left. I guess I could put negative. We'll talk about z-scores later. But negative standard deviations, it makes sense still. And so what we found is that at least 88.89% of the data will be here between this value and this value. And then the rest, I guess the remaining, what's left? 11.11? Is it 11.11% would be on the edges. 100 minus 88.89. Yeah, 1111. So this is the idea behind Chebyshev's theorem. It gives us a minimum when we don't know what the distribution is shaped like. However, we've got another rule called the empirical rule. And we only use this for when we know it's a normal distribution. The normal distribution is that bell-shaped distribution where, most things are happening around the average, and then as you get further away from the average, less and less things happen. So this is the shape of the normal distribution. And the normal distribution, with the empirical rule, we get a much more accurate readings, essentially, of the percentage of values that fall within a certain number of standard deviations. And let me draw a picture here to kind of try to drive this home. Okay, so this is, I'll use sigma. That's a little better. 1 sigma, 2 sigma, 3 sigma, right? For 1 standard deviations, 2 standard deviations, 3 standard deviations. Or -1 sigma, -2 sigma, -3 sigma. And so the empirical rule tells us that within 1 standard, if it's a normal distribution, right? Very important. If it's a normal distribution, we know that 68%, approximately 68%, is going to be within 1 standard deviation away from the mean. So if we go 1 standard deviation to the right and 1 standard deviation to the left, 68% of the data will fall between those two values. That's what that's saying. Similarly, we know approximately how much lies between 2 standard deviations, and that's 95%. And finally, 3 standard deviations gives us 99.7% of the data, which is almost all of it, right? So only 0.3% of the data lie outside of 3 standard deviations away from the mean if it's a normal distribution as such. So this picture is essentially what the empirical rule is saying. Right? 68% will fall here, right? This would be 68% between these two values, which we'll learn how to find soon. Well, we pretty much already know. We know how to find sigma. You know how to find mu. These are essentially sigma away from mu, so it's either 1 plus the number of sigmas away or 1 minus the number of sigmas away if it's to the left. Okay, and so we know this, if we went from here to here, this would be 95% of the data. And if we were doing 3 standard divs from here to here, this would be 99.7% of the data. That's what the empirical rule is telling us. Again, it only works for normal distributions. If we don't know the shape of the distribution, that's when we use Chebyshev's theorem. Might as well put a star on it. It's an important theorem after all, along with the empirical rule. But I would say the empirical rule is much more important. We use this all the time. I would say try to memorize these 3 numbers. They come up quite often. The formula to get them, you don't want to know. So it's better to just memorize them, to be honest. Okay, so I've got this question here from the book. It took me a while to actually find a good question. It says here, the average U.S. yearly capita consumption of citrus fruits is 26.8 pounds. Suppose that the distribution of fruit amounts consumed is bell-shaped with a standard deviation of 4.2 pounds. So the bell-shaped here tells us that it's a normal distribution, in which case we want to use the empirical rule, right? So bell-shaped implies normal. So we want to use the empirical rule rather than Chebyshev's theorem to find this stuff that they're asking about. So what do we know about here? And then it says, what percentage of Americans would you expect to consume more than 31 pounds of citrus fruit per year? And we'll be able to figure this out using the empirical rule. So let's draw a picture. Again, we know it's bell-shaped. The picture really, really helps. Trust me. If you're having trouble with these types of problems, draw a picture. It really, really helps. So when it's a normal distribution, the mean is always right in the middle, dead center. It's X bar. This is a sample, so right. I actually think it is a population. So let me call this mu. And oh, well, we know what the number is. We know the average. The average U.S. yearly per capita consumption of citrus fruits is 26.8 pounds. So in a normal distribution, the mean goes right in the middle, as I've drawn it here, or at least tried to. And the standard deviation is 4.2 pounds. So let's try to see what one standard deviation away from the mean in each direction would be. What would this number be to the right? One standard deviation to the right, we take the mean, 26.8, and we just add the standard deviation, 4.2. So this value right here is 31. The value, one standard deviation to the left of the mean, let me just call this, I'll call this mu, so that you know what it is. And this is mu plus sigma, actually. And let me go one standard deviation to the left. So I do 26.8 minus 4.2. It's 22.6. That's this value right here. And this is mu minus sigma. And what does this tell us? It gives us the boundaries of one standard deviation away from the mean in each direction. Right? This is our mean. I'll put a dotted line for our mean. And if we go one standard deviation to the right and one standard deviation to the left, it's a normal distribution. The empirical rule tells us that this has got to be what? Remember, it is 68% of the data. So between here and here lies 68% of the data. Let's fill out the rest. So we know all the values. Then we can make our answer. So what about if we want to got two standard deviations in each direction? Well, there's a couple different ways you could do it. You could either do mu plus 2 sigma and mu minus 2 sigma. Or just add sigma to 31 and subtract sigma from 22.6, the right and left values. So 31, I have to add 4.2. It's 35.2. And 22.6, I subtract 4.2. It's 18.4. And so now we know these are the values that 97% of the data lie between. I should use a different color maybe for the next one. How about purple? Green? Maybe I shouldn't go further because it might just cause confusion. Let me erase these, actually. We only need the first standard deviations for this one. Because it's asking us, what percentage of Americans would you expect to consume more than 31 pounds of citrus per year? And that's going to be the people in this range. Right? Bigger than 31. Well, we found 31 is the right bound for one standard deviation away from the mean. And that will help us figure out this percentage. So the percentage between this, as we said, is 68%. So let me put that here, actually. And if the whole thing is 100%, and since this is a bell-shaped curve, it's symmetric on each side, we know how much is left. Well, there's 32% left to divvy up, and so we've got to split that in half to each tail, essentially. Right, so if this is 68%, let me, I guess, right here, as I mentioned, we've got 32% of the data left to divvy up here. And it's symmetric. Very important. Normal distribution is symmetric. So if you cut it in half, there's got to be 50% on the right, 50% on the left. And so what this also means is that if we've got 32% left and we've got two equal-sized tails to distribute that percentage to, we cut that in half. 32 divided by 2 is 16. So each of these kind of portions of the distribution equate for 16% of the data. And so we see here that this right tail gives us 16% of the data, so that would be our answer. Okay, and that's how we would come up with our answer. We've got to use the empirical rule. If it had like a different number here, you know, we only know the empirical rule, so they would only be using numbers with exact standard deviations. So, you know, maybe they said, how many would you expect to consume less than 22.6 pounds? That would still be 16%, right? That would be the left side of the tail. What was that other number we got? Let's do one more, right? 31 plus 4.2 would be 35.2. So that's the right bound of 2 standard deviations. Remember, 2 standard deviations encompasses 97% of the data. So we would have 3% left for each tail. Cutting that in half would be 1.5%. So we would say that 1.5% of the data would be, or I'm sorry, 1.5% of Americans would consume more than 35.2 pounds of citrus fruit per year. Similarly, I could go the left way, 22.6 minus 4.2. This would be the low bound of 2 standard deviations. So I know that it would be 1.5% to the left of this. So we would say approximately 1.5% of Americans eat less than 18.4 pounds of citrus fruit per year. So I hope this example sheds some light on those. We'll be discussing normal distributions a lot more. So and hopefully you'll get a lot of good practice in the homeworks and on the quizzes. I'm going to end this video here, and I'll start the next one up at 3.3. It's a pretty long enough video anyway. So thanks for watching, and I'll see you in the next video.